let's say you have hydrogen with 1 electron, again, this time with chlorine with its 7 electrons. And now what they're going to do is they're going to share electrons with each other. Sorry, that got erased. They're going to share electrons to form that covalent bond. And what you have is this kind of a bond. And notice carefully, we don't care about those electrons. Those are the valence electrons around chlorine. We only care about that. That is the bond. But now, in this kind of a situation, even though, I'm going to just highlight that bond, even though the bond is between H and Cl is covalent in character, chlorine actually will pull this bond more towards itself. So what you'll end up having is, you can depict this with an arrow, or let's do so in this case, the chlorine is going to pull the bond more towards itself. That's because the chlorine is different from the hydrogen, and both these atoms have different tendencies to attract electrons in the bond towards themselves. Okay, now this tendency is called electronegativity. Okay, so what we're going to do is we're going to write difference in tendency of, or let's put it this way, we can define electronegativity as the tendency of an atom to attract electrons towards itself in a covalent bond. So now once you have this kind of a bond and the electrons are being attracted towards one of the atoms, you'll end up with, so if I redraw the HCl, just the bond, this bond will actually end up leaning more towards the chlorine depicted by the arrow, and you will end up having a partial negative charge. This little sign out here is called a delta. So it's really, in chemistry, you call it a delta negative. Okay, so delta is the sign, is the symbol, and then the negative charge is depicted by negative. And then consequently, because hydrogen, these electrons are pulled away from the hydrogen, therefore the hydrogen will have a delta positive. Okay, so as you can see, this bond is now a polar bond. Okay, so we call this a polar covalent bond. All right, so if you look at the previous case where you had hydrogen connecting only with hydrogen, and one thing to pay attention to is this bond is actually made up of 2 electrons. Anytime a bond forms, you're looking at 2 electrons. Because there's no appreciable difference in electronegativity between the hydrogens, therefore these two hydrogens will not attract the electrons towards each other any more than the opposite hydrogen. Therefore, this one is going to be a non-polar covalent bond. All right. Now, the question arises, how would you know, or where should you draw the line between appreciably different electronegativity and not appreciably different electronegativity? Because if the electronegativity difference, the question arises, how would you know if the electronegativity difference between the two atoms is big enough to make it a polar covalent bond, or is not big enough to make it a non-polar covalent bond? And for that, let's show you 3 different rules. Okay, so I'm just going to put electronegativity difference, I'm just going to call it a delta. That's a delta symbol, and I'm going to abbreviate electronegativity as En, capital En. So if the electronegativity difference, well, let's just call this electronegativity difference. So if the electronegativity difference is anywhere between 0 and 0.4, then the bond is largely nonpolar, covalent. If the difference is between 0.5 and 2.1, now the bond becomes polar, covalent. And anytime the difference is greater than 2.1, now the bond is ionic. So one thing to notice out here, when the difference is really between 0 and 2.1, the electrons are still being shared between the atoms. Okay, so I'm just going to draw just two circles out here to show you. So you have the two electrons between them. So it's going to shade these circles. Okay, let's shade this one with a different color. All right. So if you have this atom and this atom, the electrons are out here. If if the electronegativity difference between this one and this one is anywhere from 0 to 2.1, then these electrons are shared between these two atoms. Now they may be shared equally. If they're shared equally, then you have a nonpolar covalent bond. If they're shared unequally, then you have a polar covalent bond. Okay. Now at anytime the electronegativity difference goes greater than 2.1, now these electrons are going to get transferred to either this atom or this atom, depending upon which one is more electronegative. So let's assume the pink one is more electronegative, therefore these two will get transferred to this atom, and that will result in a positive charge ion out here and a negatively charged ion out here. And then the bond changes from a polar covalent to an ionic bond. Okay, let's take a look at a few examples. So let's say you have the bond, a molecule HF, and you're trying to figure out if HF is going to be apolar, if the bond between H and F is going to be polar or non-polar. So let's go ahead and you'll have to look it up there is an electronegativity table or an electronegativity chart where you'll find the values. Usually most textbooks have those values. So the values for hydrogen is 2.2, and the value for fluorine is 4.0. Okay, the difference between these two values is actually, so I'm just going to depict that as delta En, and that is equal to 1.8. That difference falls under this category, and therefore this bond is going to be a polar covalent bond. All right, so let's take a look at the next example, which is oxygen. So oxygen is the same element. So you have a bond between the two oxygens. And it turns out there are actually two bonds, but it doesn't matter because the electronegativity difference between the oxygen should be the same because it's the same element. So therefore, we're going to do delta En is equal to 0. Therefore, this is going to be a non-polar bond. And finally, let's take a look at potassium fluoride, Kf. The electronegativity of K is 0.82, and the electronegativity of fluorine is 4.0. When you subtract the two, let's go ahead and do it. That is equal to 3.18. Clearly, 3.18 falls under this category. Therefore, this bond is ionic. I hope that made sense. Thank you for watching.